Each year, the Institute of Mathematical Statistics has a number of what they call Medallion lectures, special lectures that are given for excellent researchers in probability and statistics. And they name them sort of centrally, but then they assign them to different meetings. And we're lucky to have 2 Medallion lecturers at this meeting. The first one is Etienne Pardoux. He received his PhD in 1975 at Université Paris-Sud, Orsay. And after spending some time at CNRS, he took a position at Université de Provence-Marseille, which is now Aix-Marseille Université, and where he has stayed his career and as a professor for most of that time, and as of 2017, has the title of Professor Emeritus. Among his awards are the Montiel Prize from the French Academy of Sciences. Now, many of us know him for his work in stochastic PDE, nonlinear filtering, anticipating stochastic calculus, backwards SDE, homogenization, but his most recent interests, the last couple of years, I guess I would say, have been more toward evolutionary biology and epidemics, and I think that's what we're going to have. Before I give the title, I would like to have a presentation of the medallion, which is one thing for the medallion lecture. So, the light's better over here. Now we're happy to have Professor Pardoux speak on fluctuations along the law of large numbers and extinction of an endemic disease.
Thank you very much. I am very much honored by this distinction. So, as said, I want to talk about how the fluctuations around the law of large number can explain extinction of endemic disease. So I will mainly focus on homogeneous models, but then I will speak about household models, very recent work with Raphaël Forien, and at the end, if I have time, I will say a word about spatial patch models. Okay, homogeneous models. So let me, maybe not all of you are familiar with epidemic models, so let me introduce the notions, the basic notions. So we consider in particular, in my talk, I will consider only epidemic models with a constant flux of susceptible individuals. Okay, and that constant flux of susceptible individuals can come from at least 3 reasons. Either when an infectious recovers, he gains no immunity. So this is the SIS model. So after being susceptible, an individual becomes infectious and then becomes susceptible again. The other possibility is that this is the SIRS model. An infectious, when he recovers, he becomes recovered or removed and immune. But he loses his immunity after some time, so he becomes susceptible again. And the last possibility, there are, of course, other possible models. This is the 3 ones I want to present. The last one is SIR, where after being infectious, an individual, when he recovers, remains immune forever, but thanks to demography, birth, or immigration, there is a constant flux of susceptible. Okay, so first, how does the SIS model look like? Okay, the deterministic model looks as follows. So let's look at so S and I are proportions, so proportions in the total population of respectively susceptible and infectious individuals. So the proportion of infectious increases when, of course, there is new infection, and the new infection happens at rate lambda times the product of S and I. And then each infectious individual recovers at rate gamma, so this gives a minus gamma I, and of course S prime is minus I prime, so S plus I is constant equals to 1, And therefore, we can write an equation for I alone. So let me define Z to be I. So S is 1 minus Z. And the equation becomes Z prime equals lambda Z 1 minus Z minus gamma Z. Okay, so the stochastic model for the proportion of infectious individuals reads as follows. Znt equals Zn0 plus 1 over n. Okay, capital N is the total population size. There was nothing like this in the deterministic model, but in my stochastic model, capital N is the total population size, which is going to go to infinity, and we will get this equation in the limit. So each time there is an infection, of course, the proportion of infectious increases by 1 over n, and each time there is a recovery, the proportion of infectious decreases by 1 over n. So this term is clear. Each infectious recovers at rate gamma. So the proportion of infectious is Z. The number of infectious is n times Z. So this is the total rate of recovery. Now concerning the infection, you see n times Zn is the total number of infectious. So suppose that each infectious meets other people at rate lambda. Then when he meets someone, he chooses that person uniformly at random in the population. This is the idea behind the homogeneous model. And now, now the probability that the person encountered at random is susceptible is a proportion of susceptible. So it's 1 minus Z. So this explains this term. Now, one last comment about this equation is that you may wonder whether using Poisson processes, I forgot to say the most important thing, that of course, but maybe not of course for you, P-inf and P-rec are two mutually independent standard Poisson processes, rate 1 Poisson processes. I should have said that at the very beginning, sorry for that. And now, is it a good idea? Is it reasonable? Is it a good model to model this epidemic using Poisson processes? Now, concerning the infections, this is quite fair. I mean, nobody really proposes something different. But concerning the recovery, that means that the duration of infectious period is a random variable with exponential law. And this does not really fit the reality. And but we make that assumption because we want the Markov model. Okay, so now the next thing is the SIRS model. So it's very similar to the previous one, except that those the infectious will recover, they become recovered or removed. So they go in the R compartment. Okay, by the way, this is called compartments, SIR compartments. And the recovered individual lose their immunity at rate rho. So this gives it minus rho R and plus rho R here. And of course, the stochastic SIRS model, it's like this. Now we have 3 independent Poisson processes, one for infection, one for recovery, and one for loss of immunity. And clearly, one could write a 2-dimensional model for both those two systems, because the sum of the 3 proportions is 1. Next, SIRD model. Now, the SIRD model, in this model, recovered individuals remain immune forever, but there is a flux of susceptible individuals by birth at rate mu multiplied by n, while individuals from each of the 3 compartments die at rate mu. So that's the deterministic SIRD model reads like this. So S prime is mu, the birth, minus those who become infected, minus those who die. And something similar with I, minus mu I, and the recovered, they die also at rate mu. And I can write the stochastic variant of this. So now I have a little more Poisson processes, PI for infection, which appears here. Now the birth Poisson process, the death of susceptible, the death of infectious, and the recovered. And I have not written the R equation. I can just, there is no feedback of R on the other equation, so I can just write this as a two-dimensional system. Okay, maybe you may question about the fact that here I have births at rate mu times n. Maybe you think it would be more natural to have births at rate mu times the total population. But if I do that, the total population would be a critical branching process which would die in finite time almost. Surely this is not what I want. So this is why I choose to model it this way. Not only me, but everybody does it this way. Okay, so all those models can be written. So here, the Z and T will be RD valued, may be written as some initial condition plus 1 over n times the sum of hj pj of n times integral of beta j of dns ds. Okay, and now if I define mj of t to be pj of t minus t, and b of z to be the sum of beta j of z times hj, then this then this becomes exactly the second relation. Okay, so we always like martingales, so I have taken out the mean, the sort of the drift. This is the drift, and this is the martingale term. Okay, so the 3 particular cases I have considered before, it's not necessary to read all these, just, of course, in the SIS case, d equals 1. In the 2 other cases, d equals 2. The 2 important things to notice is that all coordinates of the hj vectors are either 0, 1, plus 1, or minus 1. And the second thing is that each beta j is a non-negative function, and it vanishes when you reach one of the boundary of the domain where the process takes its values. Okay, so again, this is what was written on the previous slide, and there is an alternative formulation which is equivalent. The process is the same law, which is as follows. These script mj are IID Poisson point processes on R2+, with mean the Lebesgue measure, and script mj bar is a compensated script mj. So, okay, so I guess it is clear that those are equivalent formulations, and this is more convenient for most of the proofs. Okay, so I need to introduce the notion of basic reproduction number, R0. So R0 can be, at least in those models I've talked about so far, can be considered as the mean number of individuals that an infectious individual infects while all other individuals are susceptible. So during his infectious period, he will meet a certain number of people and assume all those are susceptible. He meets no infectious, so then what is the mean number of people he will infect? So in the SIS and in the SIRS models, this R0 is lambda times lambda divided by gamma, because 1 over gamma is the mean duration of the infectious period. And the SIRD model, it's lambda divided by gamma plus mu. Okay, if R0 is less than or equal to 1, then no large epidemic. If you start with a few initial infectious, there can be any large epidemic. It's like branching process which dies out in the subcritical and critical case. If R0 is larger than 1, then the large epidemic may result from a few initial infectious. It's not necessary, but it may happen. In addition, once a major epidemic has started, if R0 is larger than 1, then in the deterministic model there is a unique endemic equilibrium. However, in the stochastic model, the disease-free equilibrium is an absorbing state which is reached sooner or later. But how much time does this take? Maybe it takes such a long time that the epidemic continues for almost forever. So this is what we want to discuss in this talk. Okay, so I need first to state the law of large numbers. So let me formulate assumptions which I will assume to be true during all the talk. So I assume that all the beta j's are locally Lipschitz and bounded, and that B is C1 and its gradient is bounded and Lipschitz. So this is easily satisfied in my model, except that in the last model with demography, the process does not stay in a compact set. So in order to have these assumptions satisfied, I need to stop the process when the total population gets too large. But okay, this is not a big problem. I mean, this is just some minor technical difficulty, I mean, not serious difficulty in some of the proofs later. Okay, so the law of large numbers says the following. Let Z and T denote the solution of the above SDE starting from Z curly n. So what does this mean? So I start here this ODE from some point in RD plus, and but I want my process ZNT to start from a vector whose coordinates are integer divided by capital N. If I don't do that, the process may jump over the boundaries. I mean, it might create serious problems. So what I denote by curly n, this is the closest vector of the form I just said to Z. Okay, so when ZNT converges, then under this assumption, ZNT converges to ZT almost surely, locally uniformly in T, where Z solves this ODE, and for that theorem to be true, I only need the beta G to be locally Lipschitz, nothing plus this ODE. I need to assume the ODE does not explode in finite time. And the main argument in the proof is just the very standard fact that if P is a standard Poisson process, P of NT divided by N converges to T almost surely as N goes to infinity, and this is locally uniformly in T. Okay, next we have a central limit theorem. If I define u nt to be square root of n times z nt minus zt, then as n goes to infinity, u nt converges weakly to u for the topology of locally uniform convergence, where u is a Gaussian process, and it is the solution of this linearized equation. Okay, we have the original, the ODE linearized plus noise, and this noise, of course, in the limit is of Brownian motion. So the BJs are mutually independent standard Brownian motions. And here, of course, I have those square root of beta Gs. Okay, so now I want to discuss something which is sort of taken from a paper by Nezel and a paper by Anderson and Britton. Central limit theorem and extinction of an epidemic. So suppose we take the SIRD model, so it is this model. So we assume that R0 is bigger than 1. In that case, it means lambda larger than gamma plus mu, in which case there is a unique stable endemic equilibrium, and which you can, of course, compute it easily. It is this vector. Okay, by the way, in all the talk, the first coordinate of Z will always be the proportion of infectious. Okay, now, the basic reproduction number is this ratio, and the expected relative time an individual is infected during his or her life is epsilon, which is 1 over gamma plus mu divided by 1 over mu. Okay, it's this, but I prefer to look at it this way because what is 1 over mu? 1 over mu is the mean life length of an individual, let's say 75 years. And what is the numerator? The numerator, well, you can forget about the mu because mu is much smaller than gamma. So it depends, of course, on the particular illness, but for some illnesses, 1 over gamma will be like 1 week. So 1 week divided by 75 years is quite small. Okay, and now I star, it's obvious that I star is less than or equal to epsilon, which is very small. Now, at equilibrium, the proportion of infectious is roughly Gaussian with mean I star, the endemic equilibrium. And the variance, okay, in this model, it's possible to show that the, the variance of u, the asymptotic variance as t goes to infinity of ut in this model is roughly 1 over r0. Or, okay, it's better approximated by 1 over r0 minus 1 over r0 squared, but let's take a rough value, 1 over r0. So it's now of course, there is this factor 1 over n. This is of course the variance, okay? Now, of course, if you have a Gaussian random variable, if its mean and its standard deviation are of the same order, you may expect that there is a significant probability that the random variable hits 0, okay? Or if you like, of course, it's not a random variable. Here I have a process, but here I have a process which for large t has this, the marginal laws are like this. So if this has the same order as the square root of this, then, or even something like 2 or 3 times the square root of this, then you can expect that the process hits 0 in time of order 1. So the critical population size, for which this, what I just said is correct, is this quantity, 1 over I star squared R0. And for n less than this critical population size, we expect extinction to occur in time of order 1. Now, in the case of meals, you can compute R0 is known, etc. Everything is known. So NC is roughly 1,000. I'm sorry, 1 million. 1 million. And now, so you expect that, okay, if you think of history, if you go back to the time where there is no vaccination of meals, then you expect that in communities which are of size smaller than this, probably the epidemic will not last very long, while if in communities whose size is significantly larger than this, you expect the epidemic to last quite long. And this, historically, this was, I mean, the first case is Iceland, whose total population is much less than 1 million, and the other case is Great Britain, and there is some indication in the book of Anderson and May about that. So somehow the history confirms this argument. Okay, now that we have discussed central limit theorem, let's go to moderate deviations. Okay, if you, in fact, I first looked at large deviations, but now that you understand that in certain cases the central limit theorem can explain extinction, maybe it's nice to look at things intermediate between central limit theorem and large deviations, which is moderate deviation. So I first describe moderate deviations, and then I will speak about large deviations. So the idea is that, so the central limit theorem describes fluctuations of the order of n to the minus 1/2. Moderate deviations describe fluctuations of order n to the minus alpha, and we can do that for any alpha between 0 and 1/2. So I fix alpha between 0 and 1/2, and of course this alpha is arbitrary. We can choose it as we like. And for each alpha, you can do the analysis. So now, if we want to understand fluctuations of the order of n to the minus alpha, it is natural to start our process from, okay, it's deviations from z star. Okay, so I want to understand moderate deviations of z and t from z star. So now it's natural to start my process from a point which should be something like z star plus n to minus alpha times z, where z is arbitrary. So again, like before, I don't take exactly this, but I take the curly n of this guy. And now moderate deviation, those moderate deviations consist in large deviation of n to the power alpha times z nt minus z star. And this I call z hat n alpha t. Sorry for the complicated notation. Where with some zn close to z, so zn is, okay, zn is almost z. If there were not this curly n, zn would be exactly z, but okay, so it's almost z. So then z, okay, I have the equation for zn. The equation for z star is trivial. I take the difference, I multiply by n to the power alpha, so I get an initial condition plus, now the drift, I expand the drift. So I write the drift as there is a first order term which is gradient b at point z star times z hat n alpha s ds plus an error term which is easy to write, but okay, it would take too much space, you know. We are limited on, and you don't, I mean, there are probably too many formulas, equations in my talk, so this you can guess by yourself what is this, and then plus the martingale term, which of course has been multiplied by n to the alpha. So the martingale term y t n alpha is n to the alpha minus 1 times this quantity. Okay, so now the basic starting point for moderate deviation here is the following. So let me define an to be n to the 2 alpha minus 1. So nu is a d-dimensional vector of sign measures. And I look at an log expectation exponential of an inverse nu of y n alpha. The fact is that this converges as n goes to infinity to 1/2 expectation of nu of q squared, where q is this guy, where you see q looks like this without, you take n equals 1 here and you replace zns by z star. Okay, how do you prove this? Well, if you don't really put here y, but an approximation of this y, which is obtained by replacing zns by z star, then it is an easy computation because this, it is easy to see that this is a sum of n mutually independent random variables and IID random variables, I'm sorry. So the computation is easy in that case. Now you have to show that when you do that correction, it makes no big difference. It's still true. This is some work which is a little more complicated than the first computation. And then, in addition, I want this result to be true when I replace y by the sum of y plus the error term. Okay, so you have to show that it makes no difference in this limit. Okay, it's a little more complicated to treat the error terms than the difference between the two things I just discussed before, but this can be done. Okay, so once we have this, essentially we can use the Gertner-Ellis theorem. Okay, what I mean by the Gertner-Ellis theorem, in fact, it's an infinite dimensional extension of the Gertner-Ellis theorem. It's one corollary in the book by Dembo and Zaytouni, which says that, okay, provided you have this plus exponential tightness, then you deduce that y and alpha obeys the large deviations principle with speed an and the good rate function lambda of phi, which I write only in the SIS case because it's simpler. I don't want to write complicated formulas. Okay. Here there is a small caveat that, okay, there is a small difficulty that my process takes values in the space D, in the scored space D, okay, because it's discontinuous. If I equip D with a scored topology, I have the problem that I don't have a topological vector space. And this Gertner-Ellis theorem applies to topological vector spaces. If I put the subnorm topology, then I am embarrassed with the exponential tightness. So the solution, one solution at least, is to approximate y by something which is continuous and piecewise linear, and which is exponentially equivalent to this. Okay, I'll say exponentially equivalent. Okay, for those who know a little bit of large deviations, essentially it's a property which says that once you prove if two sequences are exponentially equivalent, if one obeys the large deviations principle, then the other one obeys the large deviation principle exactly with the same rate function. Okay, and now that we have this, you see, I said that in fact I have this result with y replaced by this sum. So I even have the result of the first half of the next slide for this right-hand side. And now this is forcing an ODE. Now the fact that this depends upon n is really absolutely nothing. So essentially forget about the dependence upon n here, which is very well controlled. So this is forcing an equation which doesn't depend upon n, which is a linear equation. So the map which from the right-hand side to the right-hand side associates the solution of the equation is of course continuous, so we can use the contraction principle, and we deduce that d hat n alpha obeys the large deviation principle with speed an and the good rate function which is EZT of phi, which is this guy, so lambda, the same z lambda, but not evaluated at phi, but evaluated at phi minus z minus the drift. If you like, you can think of this as a controlled equation. So this is a control, so the rate function is sort of a certain norm of the control needed to get the function phi as solution of the equation. Okay. Now, from this I can deduce, from this small extension of this, I can deduce a Wenzel-Freidlin type of result, which is as follows. Let me define V of z prime t to be the infimum of IZT of phi, infimum taken over all functions phi, which start at time 0 from z and end at time t at z prime. And then V of z prime is infimum over t of V of z prime t. and now V bar A is V of 0 minus A times E1. So E1 is a vector whose first coordinate is 1 and all other coordinates are 0. Recall that the first coordinate is a proportion of infectious individuals. Okay, so in the SIS case, this guy is exactly lambda over gamma A squared over 2. So again, I recall that AN is n to the 2 alpha minus 1. Now I defined the first time that this renormalized process z hat n alpha z, that this means the first component of this guy, the first time the first component of this guy gets below minus a. Now if I take a starting point z, which is such that z1 is larger than minus a, then for any eta, the probability that this stopping time is between e to z an minus 1 v bar a minus eta and e to z an minus 1 v bar a plus eta, that probability tends to 1 and then goes to infinity. And also this guy, I have a similar result for the expectation of that time, and it can be expressed like this. Okay, and now we can discuss again the critical population size. That is, what is the population size which is such that such a deviation may explain, may mean extinction. Okay, and so this critical population size associated to alpha is 1 over Z1 star to the 1 over alpha. So roughly, of course, I don't have the R0, which I had in the CLT case, but roughly this is the critical population size for the central limit theorem raised to the power 1 over 2 alpha. Recall that alpha is less than 1/2, so 2 alpha is less than 1, so 1 over 2 alpha is greater than 1. Of course, because we expect the modal deviation to explain extinction for larger population sizes than the central limit theorem. Okay, now let's discuss large deviations. Now we want to have no limit in the population size. So let ACTD denote the set of absolutely continuous functions from 0t into RD. So for such a function, I define AK of phi, the set of C's which are L1 with values in Rk with all components non-negative, which are such that Cj of t is 0 almost everywhere when beta j of phi t is 0, and which satisfies this, d phi t dt equals sum of Cj of t h j. You see, if phi would be a solution of the ODE, of the limiting Lagrange numbers ODE, it would mean it would satisfy this, but with Cj of t equals exactly to beta j of phi t. Okay? So somehow we use this to describe the rate function for the large deviations principle. So somehow the rate function will be finite only for functions which are of that form. So which are not too far from being solution of the ODE in some sense. Okay, now this is the definition of the rate function. It of phi is infimum over the C's like that of it of phi c, where it of phi c is an integral of a sum of those guys where the function g of nu omega is nu log of nu over omega minus nu plus omega. So, okay, this is typical of Poisson large deviations in a sense. Maybe, okay, the one thing I want to say at this point is that it's not obvious from this representation of for this definition, but the fact is that this is non-negative, and this is 0 if and only if phi solves the ODE. So this is, and so somehow this can be understood or interpreted as an energy needed for keeping phi away from being a solution of the ODE. So the ODE is always a Lagrange number limiting ODE. Okay, so the large deviation statement is as follows. So I define for a subset A of trajectories, I define ETZ of A to be the infimum over phi in A, phi of 0 equals z of it of phi. And for any open subset O of the space D, lim inf of 1 over n logarithm probability that Dn belongs to O is greater than or equal to minus itz of O. And for any closed set, I have the complementary statement with lim sup less than or equal to blah. Okay, so this is quite not too surprising. Yes, I wanted to make one comment. Okay, the only difficulty in this result is the lower bound. In fact, the upper bound was known for quite some time. There is one paper by, okay, I don't remember. Paul Dupuis is one of the authors, but it's 2 or 3 authors' paper in the analysis of probability. And, but it treats only the upper bound. It says large deviations, blah, 1 upper bound. And I have never seen 2. But there is a problem with the lower bound due to the fact that the rates may vanish. If the rates would be bounded away from 0, then the result would, you could find it in several monographs, for instance, in the book by Feng and Kurtz. But due to the fact that the rates may vanish, there is some difficulty for the lower bound. So there is one paper by Schwarz and Weiss, motivated by quite different assumptions from ours, which does this, but with assumptions which are too strong for us. So I have developed with my students and courses, in fact, 3 different approaches. One extends an argument due to Dolgo-Archinnik, and another adapts to Poisson point processes driven SDEs, a quasi-continuity argument due to Azencott in his Saint-Flour lecture notes, and Priore also expanded a little bit the approach, but that was for Brownian-driven SDEs. Okay, so now a slight reinforcement of the above result allows us to conclude the Wenzel-Freidling type of result. Okay, so I assume, of course, that I'm in a situation where the law of large number limiting ODE has a unique stable equilibrium Z star, the endemic equilibrium, whose, of course, first component is strictly positive. And I define again a quasi-potential. Here it's simpler to define. So V bar is the infimum over T, infimum over all phi in ACTD, which starts from Z star and which end at a point where the first component is 0. So the infimum of IT of phi over all. I mean, first I take, for fixed T, I take the infimum over phi and then infimum over T. And now I define the time of extinction, which is the first time that the first component of Z is 0, starting from, the extinction time depends upon Z, and the Z is here, okay? Still the same definition for this curly NZ. Okay, so the result is that the probability that the extinction time is between those 2 exponentials tends to 1 as n goes to infinity, and I have similar statement for the expectation of the stopping time. By the way, the proof, okay, once you have the large deviations result with some uniformity in the starting point, I mean, the proof follows the same arguments as you can find, for instance, in Dembo and Zaitouni concerning Poisson-driven SDs. You just have to make small modifications because your processes jump, but it's no big deal. Okay, now the important thing for me is that in the SIS case, I can compute exactly V bar, okay? Because when you have something like this, okay, exponential n V bar can be huge, depends of course upon n, but it depends also upon V bar. If V bar is very small, then okay, but so the value of V bar is important in such result. And only in the SIS case, we have an explicit formula for V bar, and it is log lambda over gamma minus 1 plus gamma over lambda. Okay, so now I want to stress a comparison between central limit theorem, moderate deviations, and large deviations. And I do that for the SIS model only because this is the only case where I have explicit formulas. Okay, so in the central limit theorem, in the SIS case, the asymptotic variance is gamma over lambda. From very standard estimates on Gaussian random variables, you deduce that for any eta strictly positive, there exists T and n large enough such that the probability that square root of n times z nt is larger than a is less than this exponential. Now, for moderate deviations, you have essentially the same statement with exactly the same form here, but here you replace square root of n by n to the alpha, and here, of course, appears the power of n, which is n to the 0 when alpha equals 1/2, so CLT, but for moderate deviations, you have a power of n. And the large deviations result, okay, by making, okay, all this, you need a small computation from the formulas I have given above. The large deviations result tells us that at least if A is less than gamma over lambda, the probabilities that dnt is larger than A is less than this exponential. Okay, so you see that here the form of the function of A is quite different. However, if you do an expansion near 0 for small a, then you recover lambda A squared over 2 gamma. By the way, it turns out that the fact that the discontinuity in the formulas here is exactly for alpha equals 0, that is at large deviations, is typical of light tails. If we were dealing with random variables with heavy tails, probably the discontinuity would be somewhere else for alpha, somewhere else between 1/2 and 0. And the last point is that, okay, so this is a probability that this kind of deviation, probability is that this type of deviation, this is a probability that this type of deviation happens, but in fact this happens in time e to the n to the 1 minus 2 alpha v bar a. Okay, so somehow you can connect all those results. Okay, now I want to go to household models. I don't have much time left, but so I consider now a SIS household epidemic model. So in this model, I have, okay, this is sort of the first natural model beyond homogeneous model. Okay, so here we assume that we have n households with sizes nu1, nu2, nu_n, where the nu i's are IID n-valued random variables. So the xni of t denotes the number of infectious individuals in the ith household at time t. We suppose that each infected individual can infect another individual within the same household at rate lambda L for some lambda L strictly positive. The individual to be infected is chosen uniformly from those in the household, and if he or she is already infected, nothing happens. And moreover, there is also each infected individual infects another individual uniformly chosen in the total population at rate lambda g. Okay, and finally, everybody recovers at rate gamma. So the literature on household models goes back to 1950s, but I recommend mainly this paper. So, but the point of view we have here is quite different from what has been done before. So let script x be this set. So the n stands for the size of the household, k for the number of infectious individuals in the household. So I formalize what I have said in the previous slide as follows. So I assume that the square of nu is integrable. So I have mutually independent standard Poisson processes, which are also independent of the initial condition. And for n larger than or equal to 1, let xn1, xnn be the solution of the system of SDEs, which is like this. So you see, okay, this is no surprise. It's similar to what we had before. This is a proportion of infectious in the household, in the ith household. So 1 minus this is the proportion of susceptible. So it's not surprising to have this term. Now this is the local infection, and this is a global infection. So you see, forget about, you can cancel, there are two 1 over n's which you can cancel. Forget about this and forget about this one. Then this is the total number of infections in the total population, and this is sort of the probabilities that they choose the ith household for the infection. Okay, so this we call the SIS model, household model with n households, and this, you see that the interaction between the households is of mean field type. And so it's not surprising, so when mean field type, you may think of the Saint-Flour notes of Ansel Snitman, 1991. So assume that the initial conditions, those are IID, and that again, nu1 is square integrable. Then let this system be the solution of the above equation. I take the empirical measure, 1 over n sum 1 to n of delta nu I x n I. This converges weakly to a certain measure mu as n goes to infinity in probability. And moreover, I have propagation of chaos in the sense that those, of course, for each n, those are not independent. They are correlated, but as n goes to infinity, the k first become independent in the limit. Okay, and now the limiting equations. So we have nonlinear Fokker-Planck equation. Nonlinear because there is this term which is, okay, maybe I should write immediately. Okay, let me look first at what I call Makin-Vlasov type SDE. So it is a Poisson-driven SDE where the evolution depends not only upon the position, the value of x at time s, but also upon its probability law through the mean expectation of x, which replaces the 1/n sum of x and I in the approximation. Quite standard. And clearly, if this has a solution, then the evolution of the law of this process should be given by this Fokker-Planck equation. I mean, this is quite obvious. And of course, what I mean by that is that mu n k of t would be the probability that nu equals n and x of t equals k. Now, if the support of mu, the law of nu i's, would be finite, then this would be a finite dimensional system of ODEs which you could solve because the coefficients are locally Lipschitz, unique solution, and then you get the law of x, then you can compute this, and then you can solve this equation. But this is not the case, so we have to devise another some method to solve this equation. It's not obvious to prove that you can say either this has a solution or a unique solution, or this one is sort of equivalent to solve the two. So the method we use is if we replace the expectation of x by given function m, then we can solve the equation, and then we have to find a fixed point of this mapping. And I don't have time to give those. Okay, now I want to finish by saying something about the large time behavior of a Makin-Vlasov SDE. So here I define R0, which is the mean number of households that one initially infected households which experiences a local infection, only a local infection without global infection from the outside, starting from 1. So this is mean number of households that such a household infects. So it's given by this. We can compute it explicitly, well, explicitly through a series. And the interesting result is the following. Again, we assume the expectation of nu squared is finite. So you see here, you see appearing the size bias distribution of the households. Okay, if R0 is strictly bigger than 1, then there exists a unique probability distribution such that if we start, the initial condition has a true proportion of infected individuals, then nu x of t converges in distribution to z mu infinity as t goes to infinity. And mu infinity is non-trivial in the sense that it is not essentially delta at 0. However, on the other hand, if R0 is less than or equal to 1, then x of t goes to 0 in probability as t goes to infinity. And just, oops, I skipped this. So just one word very quick about fluctuations. So far, we have not been able to treat the CLT, central limit theorem, in the case where the support of the law of nu is unbounded. So if the support is bounded, then the CLT moderate and large deviations are consequences of the results above. So we can do it. And maybe I say nothing about this, and these are the references. Thank you very much.
Because of the format here, I don't think this is the best place for questions. If anyone has any questions for Etienne, I think he'll be around for the coffee. He will be around in the coffee break, and that would be a good place to give. And let's thank him again for the talk.